Welcome back, everybody. This is our video solution to problem 3 from Quiz 7, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. All right, let's see what we got. V is going to be a finite dimensional vector space over the complex numbers, and T is a linear operator on V. We're going to assume that with respect to some basis, we'll just call it V1 through V4 of V, we have that the matrix of T is given by a matrix which is in upper triangular form. Right, so we notice all of the entries below the diagonal are 0. Right, all these nice zeros here. Okay, so what do we want to know? Well, the first says find the eigenvalues of T. So the beauty is that when we have a matrix for an operator in upper triangular form, we know that the eigenvalues are precisely the entries along the diagonal. So this is pretty easy, right? So since M of T is upper triangular, the eigenvalues of the operator T are going to be 2 plus I, 1. Notice 2 plus I shows up a second time. I don't have to write it twice, right? It's just a set. And then negative 3. Okay, next question. Determine if T is invertible. Okay, well, we know that if T is invertible, then T is injective. And if T is injective, then T is invertible, because we're working with a linear operator on a finite dimensional vector space. So it's enough to determine that T is injective. Okay, so T is invertible. This is equivalent to T is injective. But T is injective if and only if the null of T is equal to 0. All right. Well, what if the null of T wasn't equal to 0? All right, if the null of T was not equal to 0, right? So if V not equal to 0 is in the null of T, then TV is equal to 0. But 0, of course, I could write that as 0 times V, and that would tell you that 0 is an eigenvalue for T. Oh, but we already know what the eigenvalues for T are. None of them is 0. Therefore, all right, of course, by the way, just nice to know this, right? Of course, this is reversible. If 0 was an eigenvalue, then there would exist a non-zero element in the null space. So this is equivalent here, right? Saying null of T is 0 is precisely the same thing as saying that 0 is not an eigenvalue for T. Well, we know that 0 is not an eigenvalue for T, therefore T is invertible. All right, finally, we want to explain why for k between 1 and 4. It's funny, I could have just written 2, 3, 4. We have T of the span of the vectors between v1 and vk is contained in the span of v1 through vk. All right, and this really just comes back to how does this matrix correspond to the operator T. So remember, we can label along the top with the basis, and then we can label along the side. And the meaning of this matrix is that if I apply T to V1, T to V1 is going to be 2 plus I times V1, which is certainly in the span of V1. Right? It's just a multiple of V1. And what if I do T V2? Well, T V2 is going to equal 3 V1, right? Coming from this 3 times V1, plus 1 V2. And this is definitely in, I should say an element of, is in the span of V1 and V2. Now notice, though, that if I take the span of V1 and V2, and then I apply T to it, this is going to be contained, right? Let's see, so if I did T of the span of V1, V2, this is equal to T of, right, well, all things of the form A V1 plus B V2, where A and B are in C. Okay, but this means I'm applying T to each one of these. But now T is linear, so this is going to be the set of all things of the form A TV1 plus B TV2, where A and B are complex numbers. But TV1 is in the span of V1, and TV2 is in the span of V1, V2. Spans are closed under scalar multiplication. Therefore, this is contained in the span of V1 plus the span of V1, V2. But anything in the span of V1 is definitely in the span of V1 and V2. So this is contained in the span of V1, V2. Okay, so this shows that when we take T of the span of the first two, we end up in the span of those two. And we could keep going, all right? So we'll have to jump down here, but if I go TV3, this is equal to negative V1 plus 5V2 plus 2 plus I V3. All right, that's coming from here. And this is contained in, or an element of, the span of V1, V2, V3. And so if I use TV1, TV2, TV3, the same argument shows that the T image of the span of all of those vectors, V1, V2, V3, will be contained in the span of V1, V2, V3. And finally, you look at T of V4, and of course, this is definitely going to just be in the span of all of the vectors. Right? This isn't terribly interesting anymore. Because this is just some element in V, actually, right? This is in the span of all of them. But that's, again, not interesting because, well, the span of all of them is equal to V. All right? So at each step along the way, all right, we're able to get, right, at this step we get that the T of the span of V1, V2, V3 is contained in the span of V1, V2, V3. And again, there's nothing very interesting when we do the last statement when k is equal to 4, because that just says that everything is in V, which it definitely is. All right, everybody. That one's kind of easier to see in some sense than it is to explain. All right. We will see you all next time with another solution.